Here's a situation that we often look at when we're studying forces and uniform acceleration and energy. And in this situation, we have an object on a tabletop. It might have wheels on it, and it might not. It might be sliding. In this case, we'll say that the object has wheels and that there's negligible friction, so that there is no dissipative energy loss, or effectively none. And we'll say that this pulley here is pretty frictionless also. Okay, we have a string over the pulley where a second mass is hanging, and this mass descends, pulling this object along with it. We have the weight of the object, the product of the mass and the acceleration of gravity. In other words, the force exerted on the mass by gravity, acting downward. And we have a normal force in response to this. The mass is pulled downward by gravity. It pulls down on the surface on which it sits, compressing the surface a little bit, or even bending it maybe, and the surface pushes back with a normal force that's equal and opposite, so that the object can remain on the surface. If we didn't have an equal and opposite force here, the object would have to fall through the surface. As long as this support here is strong enough, we will have a normal force that's sufficient to keep the object from falling down through that support. Okay, now we have the force of gravity on this mass, m2 times the acceleration of gravity, and that's the net force acting on this mass. And it's actually the net force acting on the system that consists of these two masses connected by the string. Okay, so the forces acting on the system that we just defined are this m2g, the m1g, and the normal force. The m1g and the normal force cancel each other out. They add up to 0, so that the net force is just the m2g. That net force then accelerates the system in this direction. Accelerates this down and this to the right. Now there is tension in the string. You got a tension up here, you got a tension over here. The string is elastic. When it's pulled, it stretches a little bit and then tries to pull back at both ends, and that's where these tensions come from. But that tension isn't going to affect the motion of the system, because that tension is internal. It's in the string, which is part of the system. It's coming from within the system, maybe in response to external forces, but it stays within the system. Okay, so what's the acceleration of this system? Well, the acceleration is equal to the net force divided by the mass. The net force is m2g, and the mass, well, we've got a mass m2 and a mass m1. Okay, and I guess we didn't really put that m1 in there, so let's just pen that in. Okay, we got a mass m1 here. Okay, so let's just say that the masses are 10 kilograms and 4 kilograms. 10 here, 4 here. What's that going to tell us about the system? Well, the net force in the system is going to be 4 kilograms multiplied by 9.8 meters per second squared, the acceleration of gravity, or 39.2 newtons. The mass of the system is the 10 and the 4 kilograms, adding up to 14 kilograms. The acceleration is the net force divided by the mass. We've got the net force, we've got the mass, so this is an easy calculation. And we come out with an acceleration of 2.8 meters per second squared. So that's the acceleration of this system. Little diagram here. We have initial velocity, delta t, and acceleration. If we have these kinds of information, if we know our delta t, then we can take our acceleration, our delta t, and get the change in velocity, add that to the initial velocity to get the final, average that with the initial to get the average, and I've got this wrong. This line shouldn't be there. It's actually the initial velocity that's being averaged with the final, not the change in velocity. And put that together with our delta t to get our delta s. And we can then verify if we have a delta t. We can determine option, we can determine then how far the system travels and do the whole analysis we did in the preceding video clip. Okay, so that's kind of an interesting system there.